Hi everyone, I'm Deepthi from NetApp. I'm currently working with the Advanced Technology Group, and this work is actually a joint work done by both Rukma and me, but unfortunately Rukma couldn't be here today. So what I would be talking about today is uh, with all these AI ML workflows coming into operationalization, what are some of those key data management challenges that we as storage developers or we as data architects need to be aware of or need to do something about, right? So starting off, so maybe not more than a decade back, the data was mostly confined to a data center, right? There were humans sitting on laptops or computer machines who were generating this data. But now, this entire data landscape has changed. Sure, there's still there's still application and server logs, but in addition, we have the clickstream logs. This Fitbit that I'm wearing is actually tracking every movement that I'm making here. Then our archives have grown exponentially because of the digitization of anything and everything. Our archives have grown tremendously. Social networking, I don't need to even talk about this one because I'm sure all of us are tweeting about SDC right now, right? The media content, images, movies, videos, multimedia content, it's all growing, right? And then furthermore, what we do with that data, we no longer just store it and read it when we require. We want to extract value out of it. We want to derive local insights. We want to derive long-term insights. So instead of just a data center, this data is flowing between cloud, the data lakes that we have in the private data centers, private cloud deployments, and even compute presence close to the point of data generation. And then what you see on the right over there are the sort of the pre-processing and the AI ML workflows that we need to extract value out of the data today. So in a sense, what I'm trying to say is that everything about the data is changing today. Right from the point or the way the data is generated today, to the kind of data, to the way we process the data. It has become stream-oriented. Like it or not, it has a time aspect to it. And then the whole paradigm about extracting value from data. Well, today businesses are built on data, on extracting value from data, right? And this whole change in the data life cycle warrants the need to take a relook at the new emerging data pipeline or the way data flows in this new scenario, right? Let me go over this from left to right in this figure. So let's assume you have multiple data endpoints which are generating data. However, there is a concept of an edge, which is the first point of data entry into the pipeline. Now, all of this data is aggregated and ingested into the whole pipeline at the edge node. But it is no longer a dumb node or a dumb storage. Here we want to do real-time model inferencing. We want to be able to provide local insights, right? And after that, the data flows to the core. What we refer to as the core is essentially, think of it as your data centers or private cloud deployments, which have dedicated hardware, which is a very secure domain of operation. And when data comes here, this is the whole data processing hub for your all your AI and ML routines, right? This is where the deep learning models that we talk about are trained, right? Furthermore, then the data is sent to cloud, primarily for data archival, but as we just heard in the earlier talk by Shashikant, we are also leveraging the as-a-service hosted solutions hosted in the cloud for our data here, right? So now another important aspect here is that there is a very fuzzy boundary between this core and cloud. Some enterprises, in fact, choose to build their DL or ML routines in the cloud itself. So some enterprises follow an edge core cloud sort of a pipeline, while some others stick to the edge cloud paradigm, right? Now, but with this whole new kind of a data flow, let's talk about some of the very interesting data management challenges that creep up, right? So here is a list of 5 key data management challenges which I believe are very important for us to think about in this new data flow. So performance. Now, if you talk about AI ML routines, they are performance intensive by their design. They need that performance from the compute, from the network, and all the way down the stack from the storage, right? Efficient storage. We require our storage to be much more reliable, much more feature rich in terms of being able to meet the requirements or the performance requirements of these AI ML applications. Security and compliance. Well, GDPR is coming into effect today, I believe. So I don't need to motivate compliance because the compliance landscape is changing altogether, right? Security has always been important, and it still remains very important in this scenario, because imagine if my health records are put out into the public, I am worried about it. As a user, I'm worried about it, and hence, as enterprises, companies are worried about it. Again, another aspect is the data quality. So a known saying sort of in the AI ML world is that if you feed junk into your model, what you will get out is junk. So you need to ensure that your data has some level. Now, it's difficult to quantify quality, but it still needs to be qualitative enough for me to extract anything reasonable out of it, right? So now, what I would like to do is discuss each of these 3 components of edge, core, and cloud one by one, and the specific data management challenges at each of these 3 layers, right? So coming to edge. So edge, as I said, is the part of where we try to derive real-time insights, right? For example, let's say temperature sensor in a smart office is reporting continuously high temperatures to me. Now, I need to be able to take that action locally, that I need to switch on the air conditioning or lower the temperature, right? So those are the kind of insights that I'm talking about. This is also the point where data is transferred over WAN to the core or the cloud, right? So we need to prepare this data to be transferred over WAN. And the moment you talk about WAN transfers, you talk about the cost involved, both in terms of dollars as well as in terms of the WAN bandwidth required. So we need some sort of storage efficiency over the wire. We need to transfer as little data as possible to minimize our WAN costs, right? Now there are 2 views which practitioners typically believe. One view is that we transfer very limited data, which is anytime there is a deviation in behavior from the normal behavior, that is when the data is interesting. That is the only data we should transfer. However, there is also a contradictory view which says that I don't know what data will be useful at what point in time. So I want to transfer all my data. But still, I want to minimize my WAN costs, right? So how do you do this? So what they are okay with is some sort of data approximation or a quantifiable loss. I should be able to say that this new data value that you have is within 5% or 10% or some X% error bounds of its original value, which is what I mean by the quantifiable data loss, right? So now, as a matter of fact, there is very interesting research happening especially for time series data, in terms of the data reduction, right? So there is this algorithm or research, rather I would say, which is called matrix profiles. It's done by a team in University of California. And what they talk about is alternate representation for a time series. So what you see here in the red is the time series, the actual time series that we are trying to reduce. And what you see here in blue is the matrix profiles representation for that time series. So the essential concept is that anytime there is a repeating pattern, so anytime there is a repeating pattern, like this pattern here and this pattern here is repeating, right? The value of this matrix profiles would be very low. So by looking at these matrix profiles values, you can actually identify recurring subsequences or inherent patterns in this time series. And now, once you have identified the subsequences or recurring patterns, then your time series essentially can be represented as a sequence of these repeating patterns. So basically, instead of these 20 points here, which make up this particular small part of the time series, I can just say that, hey, this is pattern 5, right? And that's the way you get to data reduction. The interesting parts, however, with this kind of an algorithm is that it's an anytime algorithm. Let's say I do not have the compute resources at the edge to continuously keep running this algorithm. So I can stop it at any given point in time and it will still give me consistent results. It's an anytime algorithm. And then it scales with hardware. It is designed in such a way that the moment I throw more GPUs or CPUs at it, it would scale its performance and I would get the benefit, right? So I don't have time to go into the details, but this was just to highlight that there is interesting research happening in this area. And people are actually realizing the importance of data reduction before sending data to the core, right? So going further to another, this is not so much of a challenge or an issue, but just an important point I wanted to bring up, that since your edge node is the first point of data entry into your pipeline, it is the best place where metadata enrichment can happen, right? For example, where is this data originating from? The geolocation of the data. It is best suited to happen here. Assessing the data quality is best here because after this my data gets transformed and it just moves through the pipeline. So I want to do as much of metadata enrichment as possible at the edge. Now what is all that kind of metadata? I talked about data quality briefly, but there are various aspects to data quality. Is my data accurate? Now how do you say accurate? Now in most deployments, especially in the IoT world, we have a lot of redundant sensors reporting the same thing. Now, if I have 4 of these sensors reporting the pressure of a particular wall, then I need to be sure that all 4 of them are reporting the same value, right? That is what accuracy means. Completeness. Most often, there is a lot of missing data that we have to deal with, right? The data is most often never complete. So that is one other aspect. Timeliness, which basically means, have I even received the data for all timestamps? Is it complete and is it timely enough? Now, there are various other metrics measuring data quality. These are just some of them. The kind of data, whether it's a video file, it's an image file, or it's a document. If it's a document, is it a financial document or is it a legal document? And so on and so forth, right? The kind of data is important. The behavior of data, which is it a very normal, commonly observed thing, or is there something, quote unquote, interesting about it? Is it different from normal? That is what anomalous or normal means here. And then the lineage and auditing data. So with compliance regulations, being able to trace the lineage of the data is becoming very important. And for that, we need to have appropriate metadata in place right from the start. So we'll talk a little more about this when we go further down the line, right? So, but why all this metadata? How does it help us? It helps us in various data workflows down the pipeline. For example, just a very hypothetical example, I might want to place all the, let's say, brain scan images in one volume just to maximize my deduplication, right? So there are various intelligent workflows or policy-based governance rules which can be built on top of this metadata. And by the way, tools like Kafka and Spark have realized the importance of this custom metadata and have added support in streams today, right, to add custom data. So going further, and let's talk a little bit about security. So security, as I said, is a major concern today among enterprises, amongst end users, and amongst everybody really involved, right? The very access controls and perimeter security at the edge. Perimeter security is commonly what we all come to know or understand as firewalls, right? Which protect our sort of, which form a perimeter into what kind of data can enter into our system. But still, there is a whole notion of security which emerges because just there are way too many endpoints. And all of them want to now transfer data to this edge node, right? So you definitely need some means of authentication. Fine, let's have a means of authentication, right? But what if I just pick up a sensor from autonomous vehicles, say, and put it into another vehicle? What happens? So you need some sort of session-based authentication. The device can't just keep transferring data once authenticated forever. You need session boundaries. And SSL certificates, which is based on public key sharing, is one way of doing that. Now, I'm not a security expert here, but this is just one of the ways. But what I want to bring out is that security is an important concern which needs to be thought of in this scenario, right? So coming to the core. So core, as I said, comprises of your private cloud deployments, your data center, which is a very secure, protected environment, and it's mostly composed of dedicated hardware where all your AI and ML routines run. And the moment you talk about AI ML, you talk about performance, right? So why is performance requirements suddenly such an important issue? First, there are many new neural network, many new deep learning, many new AI ML variants today. It has become very easy to build an ML model. Frankly speaking, today, I don't even need to understand what ML is to build my first model. I don't need to. The tools like PyTorch and Keras have made it very easy for us. They have abstracted out the sort of the APIs from the inner functionality to a huge extent. Data, there is no doubt today. We just have data available to us. And perhaps the more important factor is the prevalence of GPUs and TPUs. They have become very prevalently available, right? They're just very easy to procure today. And these GPUs and TPUs have a very high parallel massive compute, right? So imagine all these multiple GPUs reading in parallel or trying to read in parallel from the storage. So what kind of storage requirements in terms of the performance do we have to satisfy to meet these compute requirements of CPUs, right? So we require our storage to be high performance, predictable performance, because even a factor slowdown can impact my entire data pipeline of the order of days, right? So going to what can we do as to improve performance. So indexing has always been a traditional way to improve storage performance. We have known it, we have all used it, we have built indexes on various columns in our RDBMSs, right? But I have added the word smart there. Why? Because the workloads are changing. Today, I might be wanting to look at the data from a geolocation perspective. But tomorrow, I might be wanting to look at the data of only, say, pressure sensors in the system, right? So both of these queries require a different kind of indexing from the underlying storage. So if we can design dynamic indexing based on query patterns. So based on the query patterns, can we say that what columns, if I may, should we build an index on? What fields require indexing? Then oftentimes there is an update cost associated with indexing. To update the index, it requires severe compute. So how often does the index need to be updated? Should I update it every 10 minutes or every 1 hour or 1 day, or what should be that granularity? It could possibly be different for different indexes. Otherwise, also another important aspect is which indices are obsolete, which I don't need anymore. Often what happens is we build indexes and we forget to delete them. But they keep eating the compute resources due to their updation. We don't need them. So my point here is that can we arrive at decisions around these lines, around indexing, based on the query patterns in using AI or ML, right? Now, another approach to smart data indexing is what this paper talks about. The link is here. But let me take an example here. So let's say you want to store data ranging from 1 to 50 integer values into your storage. Now, a traditional index, let's say if I build a B-tree index out of this, what would happen? If I want to query for any particular point, say the number 26, I will get the location of that on the disk in log n operations. That is the complexity of your B-tree, right? But what is missing here is that B-tree is not able to utilize the inherent distribution of your data, right? I know if the value 1 is stored at offset ABC, the value 26 would be stored at offset ABC plus 26. I don't even need to go through those order log n operations. So the premise of this paper here is that can we learn the structure of the keys or the sort order of the keys to predict location of records, right? So essentially, what I'm trying to point out is that now data indexing is a very core management feature which has been there with us for a long time. But can we use AI or ML techniques to replace these core data management components to better enhance our systems, to make them more worthy of running AI ML, right? That's the play there. So going further, another important aspect the core has to deal with is the complexity of data, right? We have all seen this picture in the context of big data, the volume of data, the variety of data, structured, unstructured, text, multimedia, etc., etc., etc. The velocity of data. It is a changing data. We receive continuous streams of data, which are continuously transformed by various processing or transformation routines, just generating more streams of data. So the velocity of change is really very high. Now you have all this complex data. Now from multiple sensors, multiple edge locations, and so on and so forth. So even providing a holistic view of the data to the end application becomes a challenge. How do you effectively aggregate and how do you effectively bunch your data together to provide a holistic view becomes a major challenge. Also, core is the point where we need to transfer data to cloud, right? Cloud is an unsecure, unprotected environment. At least that is what most people believe today, most enterprises believe today. So we want to do necessary anonymization before we transfer the data, right? I don't want my, say, driver's license number going out there in plain text to the cloud. It requires that kind of an anonymization before it goes there, right? Also, various decisions about how do I want to store my data in the cloud. Should I compress it before sending it? Should I encrypt it before sending it? If I encrypt it, should I store the key metadata store on-prem? Or what should I do with it? Right? Those decisions also need to be taken here. So let's say we have taken all those decisions and the data has reached the cloud. It's primarily the archival tier, but as I said, it is also the place where some applications and some intelligent processing is done today using hosted as a service solutions out there, right? So when we talk about archival, compliance is what is governing archival requirements today, right? Compliance dictates the life cycle of data. How long should I keep the data, and how often, right, for example, the right to be forgotten clause in GDPR. So what it says is, as a user, I should be able to request my, say, data storage company to delete any records that are associated with me as a user. So now imagine the kind of indexing or the kind of metadata that you would want to store to even serve that query, right? Provenance traceability we did talk about briefly, but if something goes wrong, I need to be able to produce the entire lineage of my data. What point was it generated? How did it transform? From what, using which network resources did it move, and so on and so forth, right? Also, the whole aspect of long-term data retention. How long should I store my medical records? How long should I store my archives? And so on and so forth, right? The long-term data retention comes with its, now why is it a challenge? It's a challenge because enterprises are worried about the cost, the sheer cost that comes with long-term data retention. See, it's not data that they're using day in and day out. It's just an additional overhead to store and keep paying for just storing that data, right? And the unpredictable growth in data adds to the cost. But what can we do to manage this cost or lower this cost? So this is what we touched about in the earlier presentation as well about archival tiering, right? So your active archives are different from your cold deep archives. So for active archives, and today actually cloud providers provide different kinds of archival tiers. Even S3 itself has 3 different kinds of archival tiers. Then going further, they have Glacier Expedite, Glacier Bulk, and various others. Now, of course, across these tiers, you have a trade-off between $ per GB cost and the retrieval times, right? So based on what data you want to read and what data you don't want to read, you can choose your appropriate tier for that data, right? Now, typically in the archival scenario, enterprises choose to go with erasure coding rather than replication, again because of the cost factor. Because replication has a minimum 2x overhead in cost, while erasure coding has definitely less than 2. Now there are various erasure coding schemes you can choose, and there's always a trade-off between storage overhead, bandwidth, read times, performance in terms of compute, and so on. So maybe for your active archives, which is still serving some workloads, you might want to choose an erasure coding scheme to minimize the retrieval times. But for your coldest, deepest archives, you might want to just choose a scheme which gives you the minimal storage overhead, right? There's just one way of minimizing cost even further, apart from just tiering, right? Okay, so security. Again, we come back to security because cloud and security go hand in hand. So let's say most enterprises choose to store encrypted data in the cloud today and store their key metadata service on-premise, right? And there is a concept of VPNs, and VPCs is the domain in which they operate, and it provides a secure, trusted environment, again, right? But let's say, what happens when I want to now run some analytic workloads on this encrypted data? What happens to encryption in that case? How do I even make sense of this data? Well, to our rescue, there is work going on in the security domain around developing encryption schemes which compromise on certain aspects of security to preserve a property of data. For example, let's say my analytics application is interested in just knowing that value A is less than value B, which means I'm just interested in knowing the order of the data. It does not matter what those values are really. So to encrypt the data in that way, we have something called as order preserving encryption. Similarly, there are various other schemes which are there today, right? Or on which research is going on today. Now, I touched upon a few of the data management challenges, but these are some of the others which I believe are important, but I do not have the time to go over all of them in detail. But so storage infrastructure suitable for each of these three layers. At the edge, whether I need a key value store or an object store or a time series database, or how do I store my data? Similarly, at the core and at the cloud, and it's just that's a whole separate discussion in itself. I've not touched upon that in this presentation. The implementation of compliance regulations. So today, enterprises face a huge challenge in terms of identifying what documents or what objects should be complied to which regulations. And let's say even I have identified, but even then, how do I even verify that I am meeting the compliance standards? It's a challenge just implementing this whole compliance sort of bubble in itself, right? So I've not touched upon that aspect. The global namespace across the pipeline. So now we are transferring data from its point of generation all the way to the cloud in multiple phases. But as a user or an application, I should have a global namespace kind of view to this data. I should not have to know that, query node XYZ in the core component of the data lake. I should just be saying that for this particular time period, give me this data, right? So we need some kind of a global namespace architecture. And that is where NetApp Data Fabric comes in. And it provides a single data landscape architecture over your data centers, over the edge, cloud service providers, and the hyperscalers, while enabling secure data move between each of these three tiers, right? So in the end, I would like to leave you with some key takeaways from the talk. The whole data landscape is changing, which mandates the need for a new kind of a data architecture and a new data pipeline, the whole edge core cloud paradigm or the edge cloud paradigm. And the data management issues really remain the same, but they need we are still talking about performance, we are still talking about efficient layout, we are still talking about indexing, but they need a rethink from the context of this evolving data pipeline, right? And we also talked about some of the key challenges which pointed ones of performance, compliance, security, and efficient storage, right? So that is all I had. I can take questions. Done. All right.